All right, today we are going to be talking about some of the math that we are going to be working with in this class. So, the objectives are to estimate and convert SI units and then to recognize fundamental and derived units. Um, so, first of all, we have to define what a measurement actually is. And it's just a comparison of an unknown quantity to a known one. So, think about taking a ruler to a pencil, and the ruler is the standard or the known. And then we hold it up to the pencil to find out just how long that pencil is. And then one set of accepted standards is known as the metric system. The metric system is used throughout the world, other than the United States and a couple of other places, but even the other places who don't use it's more of a they don't just use the metric system, they use other things as well. We are the only country that does not use the metric system pretty much at all. Okay, anyway, the metric system has 7 fundamental units, and they are based on meters, kilograms, and seconds. The whole metric system is originally based on meters, kilograms, and seconds, which was originally based on the properties of water, but it's now taken on exact definitions. So 1 gram of water takes up a volume of 1 centimeter cubed, which is also known as 1 milliliter, and requires 1 calorie of energy to raise it 1 degree Celsius. A meter is a measurement of distance, and it's the length of the path traveled by light in a vacuum in 1 divided by 299,000 or 299,792,458 of a second. And a kilogram is the mass that is, which just roughly means how many atoms actually make up an object. And it's actually defined just by taking a chunk of platinum iridium that lives at the International Bureau of Weights and Measures. Yes, that is a place, which is in France. And that chunk is defined as 1 kilogram. So then we also have the second, and it is the unit of time, the SI unit of time. And it used to be based on 1/60th of 1/60th of 1/24th of a day. But that actually changes quite a bit. For example, in 2011, there was an earthquake in Japan, which had a 9.0 magnitude, and it increased the rotation of Earth by 1.8 millionths of a second. So now it is actually based on the cesium-133 atom. So you know that there are atomic clocks. It's talking about cesium in particular. We also have the ampere, which is electric current, which we do discuss in this class. We work with it quite a bit. And it describes how many electrons are flowing. And in 1 ampere, there is 6.241 times 10 to the 18th electrons per second. And then there's the mole, which I know you worked with in chemistry. The number of atoms needed to equal the atomic mass number in grams. So 1 mole of carbon has a mass of 12 grams and contains 6.022 times 10 to the 23rd atoms. You do not need to know this for this class. Okay, so Kelvin is temperature, and it was originally based on 1/273rd of the difference between absolute zero and the freezing point of water. But now we have a more accurate description based on the triple point of water. And the triple point is just when the solid, liquid, and gas phases exist at the same time at a certain temperature and pressure. So this scale here kind of shows you the difference between Fahrenheit versus Celsius versus Kelvin. So in Fahrenheit, it's really cold outside when it's 0 degrees, and it is really hot outside when it's 100 degrees. But at 0 degrees Celsius, that's only like 32 degrees Fahrenheit. And 100 degrees Celsius is really hot. It's 212 degrees Fahrenheit, whereas Kelvin is really cold at 0 degrees Kelvin. That's where it's so cold that atoms stop moving. And then at 100 degrees Kelvin, it's still cold. So it would still be a place where you would be dead if you had to exist in a temperature at 100 degrees Kelvin. It's not much. All right, this is just a slight joke because this is not true. It says Chuck Norris's body temperature is 98.6 degrees Celsius. 98.6 degrees Celsius would be really, really, really hot. A Normal person has a body temperature of about 37 degrees Celsius. Okay, so candela is the unit of measure for light, and it's usually defined as the strength of light from a single standardized candle from 1 meter away. Again, we have a more accurate definition, and I'm not going to read it to you. If you would like, you can, but you don't really need to know it. All right, so there is another system called the centimeter, gram, and second system. We do not use it in physics. I believe it's mostly reserved for medicine, but either way, it's not used in this class. So then we can move on to derived units. So all of their units are derived units, and that means they are composed of two or more fundamental units. So for example, you can take speed. Speed is just how far you travel in a certain amount of time. So how far you travel is a distance, which is measured in meters. And if you measure it per amount of time, that means you're going to divide it by the unit for time, which is seconds. So then that becomes meters per second. You used two units to create a new one, and that is a derived unit. And weight is actually similar to that. And we will talk in depth about weight as we go through the year. All right, there are metric prefixes, which I'm sure you have become familiar with. They are used to increase or decrease the size of any unit based on the power of 10. And these are actually on page 1 of your reference table. So if you look in the lower left-hand corner of your reference table, and I'll be passing out reference tables soon, but there is, if we start with nano, that is, the symbol for it is a lowercase n, and it's 10 to the negative ninth or 1 billionth. And I do apologize. I was having trouble with the formatting here, and I couldn't get it to superscript and subscript. So the superscript is represented by the caret, and then then the number. So if it's 10 caret negative 9, that should be 10 to the negative ninth, and so on. And then we have micro, which is a lowercase. It's not a lowercase, but it's a mu. It's a Greek letter mu, and that is 10 to the negative sixth or 1 millionth. And it's million and micro both start with a lowercase m. So then we come to milli, which is a lowercase m. So it's 10 to the negative third or 1,000th. And you can think of a millipede has about 1,000 legs. Not really, but it's a lot of little legs. And then centi is 10 to the negative 2, which is 100th. So there are 100 cents in a dollar, and 1 cent is 1/100th of a dollar. Then below that, we can talk about kilo, which is capital K, so it's 10 to the third or 1,000th. And a kilometer is sort of like a metric mile, so there's 1,000 meters, like 1,000 yards in that kilometer. So then mega is capital M, and it's 10 to the sixth or million. So you can think of like mega, big, $1 million winner. It's 10 to the sixth, capital M. Giga is 10 to the ninth or billion. And if any of you have seen Back to the Future, this is the 1.21 gigawatts of energy to power the flux capacitor. However, we don't say gigawatts, we say gigawatts. And then tera is a capital T, and it's 10 to the 12th or trillion. And that you can think of for a terabyte computer hard drive, which is actually a really large amount of information that can be stored. So that is the end of our presentation for today. I will see you next time.